So this question asks, if we mix two chemicals together, will a precipitate form? And they're telling you the chemical to look for, it's the silver sulfide. So what we need to do is figure out if we can get silver sulfide to form. And to do that, we need to look at the silver sulfide equation. So the silver sulfide equation, we're not interested in the silver nitrate or the sodium sulfide equations because those are going to dissociate 100%. We're interested in our solid silver sulfide. Okay. If this question here, will a precipitate form, is really asking if we can get it to shift left, because that's where the solid is. If we can get it to shift left, then we can say yes, a precipitate will form. If it's not going to shift left, then that's going to be a no. This isn't Le Chatelier because we're just mixing two things together, so we don't want to invoke his name unnecessarily. But we are going to calculate Q and figure out, compare Q and K. That's what this question is. First thing here we need to note is that we have molarity changes and volume changes. So there are different ways you can do this. You can do M1, V1, M2, V2, or you can just calculate the moles of each chemical and divide by the total number of moles. I will warn you, do need to watch out for dissociation. In this case, there is only one silver, so this is just safe to do the silver. But if there were two silvers here, you might need to double the number of moles of silver. So watch out for that, because we are interested in the ions, not the molecules. And here there's one sulfide, so that's safe to do with the sulfide as well. But there are two sodiums, so if we wanted to calculate the spectator sodium, we would have to double the moles of sodium. Okay, but we're not interested in the spectators right now. We want these chemicals. When you dilute these, you get a silver molarity of, let me try that again, 8.66 times 10 to the negative fourth. And you get a sulfide molarity of 1.5 times 10 to the negative fifth. Okay, and because these are initials and we have both chemicals to begin with, we have to figure out if we're going to go left or right. That's what's happening here. So to do that, we calculate Q. Q is like our KSP. It's the same equation, remember, silver squared. Initial, we just have that initial marker on there, times the sulfide, initial. So we get that 8.66 times 10 to the negative fourth squared, times the sulfide is 1.5 times 10 to the negative fifth, and we get Q is 1.12 times 10 to the negative 11th, and that is greater than my KSP, which is 1.6 times 10 to the negative 49th. And remember, this is this represents products over reactants, so products over reactants, and it's a ratio. And right now, I need my Q to be, it's too big. I need to bring it down to this. So if my number is too big and I need to make it smaller, I need more reactants. So when Q is greater than K, this means we need to shift left. So will a precipitate form? We've just added one more layer. We say yes. So that's all that means with precipitation, is because my precipitation reaction, my KSP is the solid on the left dissociating, any shift left is going to be a precipitate forming. So that's the extra piece we've added to this Q expression. the next logical question then is, here we've got another one, will a precipitate form? The next question is, okay, how much will form and what's the molarity of everything after it forms? And that is a much more difficult question. So first, let's break this down into three parts. Will a precipitate form? Calculate Q versus K. Then we're going to solve for the excess reactant and try to figure out how much of the chemical will form. And then we'll solve for the limiting reactant, which is, in equilibrium terms, we say the limiting reactant never stays zero. There's always a little bit that gets reestablished here. So if we can break it down into these three steps, it's going to help out quite a bit. So let's take a look here and see what happens. Step 1, will a precipitate form? We have calcium fluoride turns into calcium 2 plus fluoride 2 fluoride minuses. When we dilute these and get new molarities, find the moles of the calcium divided by the total volume, the moles of the fluoride divided by the total volume. We have 0.00375 moles, molar, we're doing molarities there, calcium, and 0.015 molar fluoride. We need molarities because that's what our K expression is in. It's in molarities. So we dilute them before we jump into the problem. Q then is going to be the calcium 0.00375 times the fluoride squared. Q comes out to be 8.43 times 10 to the negative 7th, which is bigger than the KSP. So we will shift left. So this is a yes. Yes, we will get a precipitate. Surprise, surprise, we're trying to figure out what happens after that point. So this is the follow-up question then. Yes, we will get a precipitate. How much of everything is left over? Okay, so now we're going to do stoichiometry for the backwards reaction. So calcium fluoride makes calcium 2 plus fluoride 2 fluoride minuses, so 0.00375, and then the 0.015 molar fluoride. And remember, these are already in molarities this time, so this is not moles. We've already accounted for the final volumes. You can do stoichiometry this way. What we're going to do here in step 2 is do stoichiometry to figure out how much solid we can make. We're just going to pretend like it goes 100% because we know the X values are ultimately going to be insignificant and small. So this is a good approximation to tell us how much will form if we pretend like it goes actually 100%. So this is a normal stoichiometry problem. And the fluoride is going to go by 2x. This is like a BCA table actually in this point, because we're doing stoichiometry. So 2 times 0.00375. And the calcium is then 0. The fluoride is then 0.0075 molar. Okay, and then we do have some solid here, so we could say how much solid forms plus x, so 0.00375. Now that's we could figure out the volume, we could figure out the grams, we could do lots of things with that, but that's those are the values there. This one does not affect the KSP though, so we're not really interested in this one numerically. Sometimes the questions will come up, but you know, it's there. It's just not affect the equilibrium. So here we've got, I'm going to keep making that slide smaller. Here we've got our first assumption here. This gives us how much calcium we could potentially make when the calcium runs out. But then we know, this is kind of what we did in chapter 4, right? We would say, okay, the sodium and the chloride are spectators, and then we would say, here's my net ionic equation. We're working backwards because we're in the KSP format, but this is my excess reactant. My limiting reactant is 0. So far, this is exactly what we did in chapter 4 with my limiting and excess ion reactants. Remember those big problems we used to do? It's just we're doing the stoichiometry in reverse so that we can stay in line with our KSP expression. So no big deal because reactions can go both ways. The only thing we're going to add then is we're going to take that chapter 4 problem and we're going to shift back, okay? So watch what happens here. Okay, minus x. The x's are insignificant. We don't really care about the solids. But we're going to do some equilibrium now instead of stoichiometry. If I have 0 calcium, which we just got rid of all of our calcium, and now I have 0.0075 fluoride, instead of just stopping the problem like we would in chapter 4 and saying my excess reactant is 0.0075, my limiting reactant is 0, equilibrium tells us that the limiting reactant does not, nothing really stays 0. There's always an x. The x is not going to be significant for the fluoride, which is why it allows us to do the stoichiometry in step 2, but that x value will be significant for the calcium. So this last step here just means the limiting reactant is not 0. We have to reestablish it with equilibrium. The limiting reactant is actually now an x value. So our KSP becomes the calcium, which is x, times the fluoride squared. And this is just a common ion problem, which we were doing the other day. And we get a calcium molarity of 7.11 times 10 to the negative 7th. Our fluoride molarity is 0.0075. We knew that after the stoichiometry step. And then if we wanted to, we could do the chloride and the sodium molarities as well. Those are spectators. We would do those in chapter 4. Let's throw those up there. The sodium did not change. It was equal to the fluoride, 0.015 molar. The chloride was coming from calcium chloride, so it would be actually double the diluted molarity. So 0.00375 times 2 actually turns out to be the same as the, well, one second. So 0.0075. Coincidentally, the same as the fluoride after the fluoride had reacted. But that's how we do this. So we say 3 steps now, and this is the hardest they'll get, and it's all review, but just kind of put together in new ways. Will a precipitate form? Will we shift left? Yes. How much of everything will we get? The fluoride is just a limiting reactant problem. That's my excess reactant. But my limiting reactant does not stay 0. It's an X value with the common ion. The excess reactant becomes a common ion.